David Stewart from the University of Newcastle on between the sheets, Richard's nilpotent algebras in modular algebra.
Thank you very much, and thanks to the organisers for being able to speak at this conference. This isn't just completely gratuitous innuendo, as I guess you'll see later on, but it is also a cocktail. I looked up the recipe just before coming here. So it's 1 ounce of cognac, 1 ounce of white rum, and 1 ounce of triple sec, and then half an ounce of lemon juice, and then you shake with ice and strain into a glass. So that may be the most useful thing I say today. Okay, but otherwise we'll let G be a reductive algebraic group over a field K, and K is going to be algebraically closed, and the characteristic is going to be something, and then I am going to want to talk about its Lie algebra, which will be G, and I'm probably going to want for most of this that G satisfies the standard hypotheses. So I won't spell all that out, but G so we want to exclude all the bad primes, so P is going to be a good prime. So that means that we're not going to have E8 in characteristic 5 or 3, or most of the time we won't have P is 2. And we also exclude SLP, but we can include things like GLN for all n. And the
SLQ is a P to a power, just P.
Yeah, I'm just giving some examples. Yeah, I mean any P to the any multiple of P. The reason you want to do that is to ensure that a result of Richardson holds, which is that the centralizers of elements in the Lie algebra are all smooth. So this guarantees that the centralizers are smooth, and that means that if I take the Lie algebra in the group of the centralizer of an element X, and I'm not going to think about that scheme theoretically, I'm just going to think about the sort of naive group there. So let me just put a K just to indicate that I know that I'm not doing that. So if I take the Lie algebra of the centralizer in the group, then I get the Lie theoretic centralizer. So that's just going to be all the elements in the Lie algebra which commute with your element. Okay, so that's very useful. Means that in particular, if you centralize a semi-simple element, then you end up with a Levi subalgebra. Right. So let's start defining things. So G subscript M is going to be the set of all elements in the Lie algebra such that the dimension of the centralizer in the group, but under these hypotheses it's going to be the same as in the Lie algebra, that the dimension is m of the centralizer. So that means that this is a union of orbits, all of G, all of the same dimension. And because it's the case that if you close up an orbit, you get orbits of a smaller dimension, it follows that this is actually going to be a locally closed set. So it is going to be a variety on its own merits, and I can look at its irreducible components. So the irreducible components of the GM are called sheets. Right. So when I saw this definition for the first time, I thought it was rather inauspicious. It's very simple to state, but it's not clear how many of these sheets there are or what one can say about them until you realise that you have a Jordan decomposition. So let's see how that features in this. So recall that X in G has a Jordan decomposition, and I'll write it as X is xn plus xs. So xn is nilpotent, xs is semi-simple, and they commute. Right, then let's pick a levy. So pick a levy subalgebra of G. I'll give an example of this in a second, and I'll call it L. So if I've got a Dinkin diagram of the of my reductive group, I just will pick some of those, some of the simple roots, and generate from the positives and negatives of those together with the torus. And then I want to choose also an element E0 in L, which is nilpotent. Right, so what can we say about this? We have, so the levy will have a centre. That will be a toral subalgebra, so diagonalizable elements, and because of the fact that I've put these conditions on the prime and the group, it means that the centralizer of ZL is L again. So that's not necessarily true in bad characteristic, and I'll maybe say something about that. But so L is the centralizer in the group of the centre, and it's not too difficult to see that if I let ZL reg be the set of elements in the centre such that their centralizer in the whole Lie algebra is L, that this is non-empty and it is actually open in, so Zariski open in the centre. Let me just try and give a quick example. So if I take, so I'll take just GLN and then my Levi is going to be this. So let's even just take GL8. So this is sort of very concrete. So that's going to be my Levi. And what's an element in ZL reg? So I could take, let's put ones along the diagonal and then go 2, 3, 4, 5. That will be an element in ZL reg. So because these eigenvalues are different, you're not going to get any, the centralizer of this won't give you any anything above or below the diagonal here. So you'll just pick up the centralizer of this block here, which will give you precisely the Levi. And perhaps for my E0, a nilpotent element I could pick might be so something like that. So that's the sort of setup we're looking at. And then what do I do with this? I want to form what's called a decomposition class. So so let D of LE0 be, so I'll act by the adjoint action of the group on E0 plus ZL reg. Right. So the reason that this is a good thing to do is that we can observe a couple of things. First of all, there were only finitely many decomposition classes. And the reason for that is because there are finitely many conjugacy classes of Levi's, and in the Levi's there are finitely many conjugacy classes of nilpotent elements. So there are finitely many decomposition classes. So that's a decomposition class. And there are finitely many of these decomposition classes because there are finitely many Levi subalgebras up to conjugacy, up to G conjugacy, and there are finitely many nilpotent orbits in these Levi's. In any reductive group, reductive group. That's still, I think, a fact that requires an exhaustive proof. So the fact that there were finitely many unipotent classes has a theoretical proof due to Lusztig. I think the fact that there are finitely many nilpotent orbits comes down to basically counting, writing down representatives, working out as many centralizers as you can, and just checking that you've kind of got enough of these of nilpotent elements to sort of fill out the whole nilpotent cone. In good characteristic, it's a theorem of Richardson, which I think appears in the same paper that he proves this result as well. But I think it would be nice to have a more systematic proof in general. Is there a bigger piece of chalk somewhere? Here. Right. Okay, and then we can say something about the sheets and the decomposition classes. So the first thing to observe is that if X, which we've written like this, is in a decomposition class, then xn is conjugate to E0, because it's a nilpotent element, it has to be conjugate to the E0, and the XS is conjugate to something in the ZL reg. That's, I think, uniqueness of Jordan decomposition going in there. And the fact that these two things commute means that, in fact, the dimension of the centralizer of X, well, you have to both centralize, because this is nilpotent, this is semi-simple, and they commute. It means that if you centralize X, you actually have to centralize these two bits separately. So if you centralize, and we can replace it by its conjugate if we're just interested in dimension. So we'll be centralizing something in ZL reg, which will put us inside the Levi, and then if we centralize the E0, we'll know precisely that the dimension of G of the centralizer in G of X is this number. So that doesn't change over the decomposition class, which means that so this decomposition class consists of orbits of the same dimension. And it's also irreducible because it's the image of two irreducible varieties. It's also irreducible. So it's contained in any sheet it intersects. It intersects, and therefore, so any sheet is the union of some decomposition classes. Right, but there are only finitely many decomposition classes, so there are only finitely many sheets. So there are finitely many sheets, which is good to know. In fact, that's true in bad characteristic as well. One can make all these definitions as usual. The bit that falls down is here, that you don't necessarily find that a Levi subgroup is the centralizer of its own center. So you can get, in bad characteristic, you can get what are called pseudo-Levis turning up. So the finiteness is still true, but let me just remark that in bad characteristic, centralizers of semi-simple elements can be pseudo-Levis. Sub-algebras. So an example is if you take P as 3 and then you choose the right semi-simple element, you can get L of type A2 tilde A2. So if you look at the Dinkin diagram, the extended Dinkin diagram, you sort of delete that node and you can see there's an A2 tilde A2 in there. So you can get things like that, but the finiteness statements are all the same. Right, good. So I think all of this stuff was originally introduced by Borho and Kraft. I should probably mention that what I'm going to say now is all joint work with Sasha Premet. So following, so I want to investigate these sheets and say a little bit more about them. In particular, we want to say something about how nilpotent elements sit inside the sheets. So following Borho and Kraft, and using, so they work over C. Most of the things that they need over C, which means things like using a Jacobson-Morozov triple, so an SL2, embedding every nilpotent element inside an SL2, you can replace by a theory of associated co-characters or optimal co-characters if you start from the Kempken-Rousseau perspective. That was all worked out by Premet in a paper in 2003. So following Borho-Kraft and using Premet's work on optimal, or otherwise known as associated co-characters, so we can prove a few things. So the first is, well, a nice description of the closure of a decomposition class, and I know that there'll be some people that are used to associated co-characters, so let me just give the description of it. So to get the closure of the decomposition class D, you take the adjoint action of G on, so we take not just the regular elements but the whole levy there. It's not going to be too surprising. You're going to be closing things up, so you're going to get the whole centre of the levy there. You also want to take, so for an associated co-character lambda to E0, you take all of the bigger than or equal to 2 parts of the grading, and then you also take n plus, where n plus is the nil radical of a parabolic containing L. So that, I realise, is not going to make a lot of sense to everybody, but I would just include the description so you can see what it looks like. Right. Okay. There's a little bit more to say. Right, so as G is reductive, we have a categorical quotient map, sort of GIT quotient, which is very nice. Which takes the Lie algebra to its quotient by G. So this is, I mean, you have to throw away some orbits and things, but so this isn't just the collection of orbits. It's some variety which has the proper, well, the categorical quotient property. So that if you have anything else surjecting onto this, yeah, that factors through, well, then you get a sort of unique map to here. So it sort of has that property. But one can be quite explicit about exactly what this is. If I call that F, then this is actually isomorphic to the Weil group fixed points on a torus T. So T is a maximal torus of G. And I suppose the GIT property is that if you look at the coordinate functions on this variety, it's the same thing as this. So taking the invariance under the group. And of course, because of this, we also have that we can write it in that way. Okay, so if one examines this, yes, there's one more fact I probably need to say there that is of importance, which is that the inverse image of 0 under this is actually the nilpotent cone. So all the nilpotent elements of G. Right. Okay, and so what we do is then look at what happens to the closure of a decomposition class under this map. Look at the fibers of that map. So the restriction. So F tilde is the restriction of F to a decomposition class. The closure of a decomposition class. We can show the following. So, all the reducible components of the fibers of F tilde are equidimensional. So they have dimension n minus the dimension of the centralizer of E naught in L, and if I restrict this to, if I look at the inverse image of 0, so this is going to give me the intersection with the nilpotent cone with DLE0. So this is just going to be DLE0 intersect the nilpotent cone. Then that is going to be irreducible and of dimension n minus dim LE0 plus dim ZL. Right. I think this must be, I think I must have missed this off here. So the point about this is that we know that a sheet is going to be made up of decomposition classes. Because there are only finitely many decomposition classes, one of them must be in there in an open way. So there must be an open decomposition class in a sheet, and so because of this result, it tells us that so any nilpotent orbit of the maximum dimension within this set must be in the sheet, and so that's going to be, there's only going to be, since the closure of this is going to contain the whole sheet, that tells us that there's precisely one nilpotent orbit that is in any sheet. So if I write that down, so corollary is that each sheet contains just one, so exactly one nilpotent orbit. It is still an open conjecture of Spaltenstein as to whether this is true in bad characteristic. So all of this works in good characteristic, but so open conjecture of Spaltenstein, that this is true even in bad characteristic. I wouldn't be surprised if nowadays algebraic geometry software on computers is kind of good enough at least to do the base case, which I think at the moment, so the lowest case open is F4 in characteristic 3. I think that's still open, so that might be worth thinking about. Right. But one can say, so I want to say something about induced orbits now, because this was how we ended up thinking about sheets. So I'll first describe Lusztig-Spaltenstein induction. So, start with the Levi. A Levi subalgebra. And take E0, a nilpotent element in L. I suppose, so L sits within some parabolic subalgebra as before. So let's say P is L plus N plus. And since so this well, I suppose it's not a sub, so it's coset of a subspace E0 plus N plus consists entirely of nilpotent elements. And the nilpotent orbits are finite. It means one of them must intersect densely. So one nilpotent orbit, let's call it O of E in G, intersects densely with this variety. Sorry? No, O of E, that's going to be the nilpotent orbit in the bigger thing that intersects densely with this thing. So I'll write the next thing and then it will make sense. So we write, so the orbit containing E is the induction from L to G of the orbit in L of E0. There are various reasons that Lusztig and Spaltenstein were interested in this. It apparently plays very nicely with the Springer correspondence. I'm not going to say anything about that because it's way off my radar. Well, as I'll say, there are some connections with some work that we were doing on maximal subalgebras. Okay, so what's the connection with sheets? Well, we've got this, we have this unique nilpotent orbit in a sheet, having started with a decomposition class. So if we let so DLE0 be the open decomposition class associated to a sheet S, then it turns out, so the unique nilpotent orbit in S is precisely this induced thing. Is OE, where OE is the induction from L to G of OL E naught, which is kind of pleasant. And the way you can prove this is by looking very carefully at the description of the decomposition class in terms of the grading that you get from these associated co-characters. It's not too difficult once you've done that. And moreover, so I suppose this is a theorem at some point, and moreover, we can even say something about the dimension of the centralizer here. So moreover, the dimension of the centralizer of E is equal to the dimension of the centralizer of E naught in L. Right. So that, I think, is all the theory I wanted to set up, and then say what we did. So I'll first some computations from this. We all the induction data, hence distribution of nilpotent orbits amongst the sheets has been done by mainly Spaltenstein in classical types, in all characteristics, and the case of the exceptional types had been done by de Graaf and Elashvili in characteristic 0. So there's quite a lot. There's quite a lot to write down, because if you think there's how many hundred odd orbits in E8, and well, I mean, I suppose you're not going to be inducing all of them, but if you think about the orbits in all the possible levies of E8 and having to induce them all up to E8 and saying what orbits you get, there's quite a lot to write down. But let me just write these two authors down. So de Graaf and Elashvili, so for exceptionals in characteristic 0. So this had been previously done by Elashvili by hand, but with de Graaf it was all checked by computer. And I might just say roughly how the calculation goes. So if you start with an orbit like this, if you start with this kind of setup, you've got a levy, say an E8, and you pick a nilpotent orbit in that levy. So choose a nice representative for that orbit. So choose a nice representative for E naught in L. You can always choose these things to be sums of root vectors. So just sums of root vectors. And then you look, and then you add in sort of random root vectors from n plus, and check the centralizer. And then if you get the right centralizer in the group, which you'll know by this formula, then you've found a representative for the induction. So if the dimension of the centralizer is correct, then this is a representative of the induced orbit. So I tried initially. I tried writing a program to just do the very same thing in characteristic P, but I eventually decided that the representatives that the Graaf and Elashvili had written down were so nice, it would be better to just check that they all worked in the different in good characteristic. So that's in fact what I did. So I simply checked that the de Graaf Elashvili reps in characteristic P were all okay, and what that meant is that the dimensions of the centralizers were still okay. Is still equal to the dimension of G of E, where E is so to be technically correct here, E is a mod P reduction of the DGE rep. I might just say, I mean, it wasn't a hugely complicated thing to think about. I'll just say what I did, just in case this is the sort of thing that comes up for anyone else. You obviously don't want to do every characteristic. That's going to take you too long. So you want something to see when this is, so to isolate the primes for which this doesn't work. So to do this, take a Chevrolet basis of G, just multiply, so calculate a matrix where you take, right, let's call these xi or something. Calculate the matrix of xi E expressed back in terms of the Chevrolet basis. So the coefficients back in terms of the xi's, and then what you're going to be interested in to know what the centralizer is when the rank of this matrix is different from what you would get in characteristic 0. In other words, calculating ranks of matrices is something you can do by putting it in Smith normal form. The things along the diagonal are going to be the elementary divisors. So the ultimate calculation is just to get the elementary divisors of this matrix and see what primes divide them. In this case, just observe that the primes dividing are all bad, so that all these representatives still work in characteristic, still work in good characteristic. And the result of that is that we get a complete description of the distribution of the nilpotent orbits amongst the sheets just by reading it off from the characteristic 0 case. So, so the theorem then is that the distribution of nilpotent orbits amongst the sheets is the same in any good characteristic. And I think I'll stop there.
I wonder if it's possible to compare the sheets to the algebra and look in the reductive group.
And oh, you mean yeah. So you can play this game in the group as well as you can in the Lie algebra. You're just going to start with a so you're going to swap the conjugation action of the group on the Lie algebra for the conjugation action of the group on itself. In which case you have you still have a Jordan decomposition just in terms of unipotent elements and semi-simple elements instead of nilpotent elements and unipotent elements. And then the question is, are all these things going to, is this theory going to be exactly the same for the group? I would be extremely surprised if it isn't, because in characteristic 0 you obviously have a very close connection between the group and the Lie algebra. I don't know if that's been written down, but I'd be astonished if it's not true.
Lusztig has defined a surjective map from the conjugacy classes of the dialog to the sheet.
Yeah, I mean this is of course him working on the sort of Springer correspondence and seeing the connection with the sheets. Yes, I think that's all true. These things will be very wrong in bad characteristic. You don't even have the same number of nilpotent and unipotent classes, so this will definitely go wrong in bad characteristic. But yeah, I don't know if it's been written down. I would be very surprised if it's not true, but I don't recall seeing it.